In this video, we're going to talk about solubility product, or KSP, and do an example problem that might be something that you might encounter. So, KSP represents the concentration of the product ions multiplied by each other, hence solubility product. And the reason you don't need, this is a little bit different than other K expressions because you don't have anything in the denominator. The reason for that is because when you're talking about solubility, you're talking about a solid dissolving to become aqueous ions. And anytime you have a pure liquid or a solid, you leave it out of the equilibrium expression. So you're really only looking at the product of the concentrations of the products, factoring in for the amount of the ions of each type that form. So the problem that we're going to address here is that if you mix 320 mils of 0.046 molar sodium hydroxide with 400 mils of 0.085 molar calcium chloride, will you have a precipitate? Now, looking at the ions that are going to be in solution, you get sodium ions floating around, you get calcium ions floating around, chloride, and hydroxide. Now, what would precipitate out of these? Using your solubility rules, you should predict that the least soluble would be the calcium hydroxide. You know sodium chloride is going to dissolve very, very well, and calcium chloride also dissolves very well. So, calcium hydroxide is the one we're concerned about precipitating. Now, the problem, it tells you that the solubility product for that expression is 5.5 times 10 to the negative 6. Now, looking at this expression, you see that you just have the molar concentration of calcium times the molar concentration of hydroxide, and that's a squared function. That squared function, again, accounts for the fact that when this dissociates, you're going to get 2 hydroxide ions. Now, what we have to first do then is figure out, in order to calculate molarity, we have to first figure out the number of moles of each thing we have, of each of the ions. And the ions, again, we're concerned about are calcium and hydroxide. So to look at the hydroxide, we say, oh, you had 320 mils, or 0.320 liters, of the sodium hydroxide solution, which had a concentration of 0.046 moles per liter. That tells you that you had 0.015 moles of sodium hydroxide in that aliquot that you added to the solution. Then you get 1 hydroxide ion for every sodium hydroxide formula unit you have. So therefore you have the same number of moles of hydroxide. And to calculate the molar concentration of hydroxide, we then just take the number of moles we have divided by the total volume. Since we added 400 mils of solution to 320 mils of solution, that's a total of 720 mils, or 0.720 liters, and that gives us a concentration of 0.021 molar of hydroxide ion. And we do the same thing for the calcium chloride. We multiply the volume that we had by the molarity to figure out the number of moles of calcium chloride. Then we recognize that you get 1 calcium ion for every calcium chloride. That tells us we have 0.034 moles of calcium ions, and we divide that by the volume again to establish our molarity. Then what we do is we plug those values in to our Q expression, which is going to represent, using the equilibrium expression, but at any point in time. We plug in the values, making sure to square that value, and we get 2.1 times 10 to the negative 5th. Since this is substantially larger than our K value, we can say that since Q is greater than K, it favors the reverse reaction. And in this case, that's going to be the formation of the solid. So therefore, we can say, yes, it precipitates. You have a higher concentration of ions present in the solution for calcium and hydroxide that should be allowed based on our equilibrium value.